Welcome to Ask and Learn.
The heating of a passive solar house at night is to be assisted by solar heated water. We need to calculate the length of time that the electric heating system would run that night with or without solar heating. So we assume that water is an incompressible substance with constant specific heats. The energy stored in the glass containers themselves is negligible, and the house is maintained at 22 degrees Celsius at all times. Now, the density of water at room temperature is 1 kilogram per liter, and the specific heat is 4.18 kilojoule per kg degree Celsius. These we get from our tables. The first thing we'll do in part A is calculate the total mass of the water. So the mass of the water is equal to its density, rho, times the volume, V. And we know the density is 1 kilogram per liter, and the volume is 50 20-liter containers. And so we get the total mass of the water to be 1000 kg. So we have 1000 kilogram of water to help us heat the house. Now, if we take the entire contents of the house, including the water, as our system, and knowing that the system is closed, we can write the energy balance relation. The energy in minus the energy out is equal to the change in energy of the house, delta E. Now, the energy into the house is due to the electric work done by the electric heater, and the energy out is due to heat transfer, so that's minus Q out. And this is responsible for a change in internal energy, delta U. But delta U is made up of the change in internal energy of the water plus the change in internal energy of the air in the house. Now, this is equal to simply the change in internal energy, delta U, only for the water. And the reason for this is delta U for the air is 0 because the air is maintained at a constant temperature. And so the internal energy of the air inside the house is constant. There's no change. And so we can write this. Let's write the left-hand side. Take the time derivative of the electrical work and multiply it by delta T. So we have the same term, but we just take the time derivative multiplied by the total time change delta T. And in essence, delta T is what we wish to calculate for. So W dot delta T minus the heat transfer is equal to, and we'll write the right-hand side as the mass of water times the specific heat of water times the change in temperature, T2 minus T1. So here we have our energy balance relation. Now, for the initial problem with the assistance of the solar heater, we can substitute our values. So we have the rate of change, the rate at which electrical work is being done, which is the power of the solar heater, to be 15 watts or 15 kilowatts or 15 kilojoules per second. And that's multiplied by the time that the heater will run for, delta T, minus the heat loss or the heat transfer out of the house to be 50,000 kilojoules every hour, multiplied by a total of 10 hours. And this is equal to the right-hand side of this equation. The mass of water we found to be 1000 kilograms times its specific heat of 4.18 kilojoule per kg degree Celsius, and a change in temperature of 22 minus 80 degrees Celsius for the water. Now, if we rearrange this equation, we can solve for the time that the heater needs to be switched on, and delta T is 17,170 seconds, which works out to 4.77 hours. So the heater needs to be on for 4.77 hours in the night to maintain the temperature at 22 degrees Celsius. Now, for part B, if the house incorporated no solar heating, then we can rewrite the energy balance equation as the rate at which the electrical energy does work times delta T minus the heat transfer out of the building must equal to 0. So the expression above will simplify even further, and that becomes 15 kilojoules per second times delta T minus, again, we have 50,000 kilojoules of energy leaving the house every hour, multiplied by a total time of 10 hours, and this is equal to 0. So again, we can rearrange and solve for delta T, and we find that this time, if we don't incorporate the solar heating, we have delta T to be 9.26 hours.